Welcome back. We now move on to topic 8, which is going to be covering liquids and solids. To get started, we need to talk about first what makes solids and liquids so alike, that they were to be grouped into one topic, because you notice gases are not included. Gases actually have their own topic because they behave so differently. But when you think about solids and liquids, what is it that makes them so alike? And in this first section, we're going to be talking about that very thing, which are intermolecular forces. So let's review a little bit about the states of matter so we can have a good framework when we go in. So there are 3 states of matter. Recall that there's solid, liquid, and gas. Solid particles are going to be tightly packed with a geometric structure. Liquid particles are also going to be tightly packed, but they lack that geometric shape. And so I like to think about a crowded group of people that might be at a concert, right? They're very closely packed, but there's really no order to it. And then finally there's gases, and gas particles are far apart with really nothing in between the particles. And the particles are so spread out that most of the container is actually empty space. Now, if you think about what dictates what state of matter that a substance might be in. For example, at room temperature and room conditions, water's in the liquid phase, oxygen's in the gas phase, things like that. What is dictating what state of matter that a substance might be in? Well, first of all, is something that we are probably very familiar with, and that is temperature, right? Or we could say more accurately, kinetic energy. Because when things are hot, the particles are moving faster. And when things are cold, particles are moving slower. So when we talk about what might dictate the state of matter for a substance, one of those things is kinetic energy. And that's why we see as we increase kinetic energy, which essentially means we're increasing temperature, we would expect the states of matter to go from solid to liquid to gas, right? But we're also going to learn that there's something else that can dictate what state of matter something might be in. And that is intermolecular forces. Now, intermolecular forces actually connects or ties with the whole idea of increasing kinetic energy. But intermolecular forces are another factor that we have to take into consideration to predict what state of matter a potential substance might be in. And here's why. We're going to realize that intermolecular forces are attractions between molecules. If the amount of attractions increase, we would end up seeing that particles would actually shift towards the solid phase, because the closer or more compact we can get the particles to each other, the higher probability that particles will actually attract to one another. And if the particles attract to one another, they'll end up creating those liquid or even solid states of matter where the particles are held closely together. So we're going to talk about that. But in this slide right here, we learned that states of matter depends on 2 things. One is kinetic energy, which is also referred to as temperature. It's not the same thing, but they're related. And the other thing is intermolecular forces. So let's talk about that. So let's first talk about intermolecular versus intramolecular. So they both have the key root word, which is molecular, right? But they have that different prefix, which is inter versus intra. When you think of intra, like you may have heard of like intranet, as some of your companies that maybe you work at have. Intra means within. So when we say intramolecular, we mean within the molecule. So intramolecular forces are really the bonds that hold the actual molecule together. This is what we learned about in topic 5 with ionic, covalent, but then we're also going to learn in this topic metallic, because there's metallic bonds as well. But these are what hold the molecules actually together themselves. Versus intermolecular, which is what we're going to talk about in this topic. Inter, you may, like for example, internet, right? The prefix inter means between. And so an intermolecular force are bonds or forces that are between molecules. And these are actually what give the molecule or the compound its specific properties, such as melting point and boiling point. So if we were to look at an example, down below here I have 2 hydrogen chloride molecules. The bond that actually holds them together, the hydrogen and the chlorine, that's the intramolecular force. That's the covalent bond, for example, that we learned about. And that's very strong. But there's also this attraction between two hydrogen chloride molecules. And this attraction is what's known as the intermolecular force. Now notice, relative to each other, the intramolecular force is much stronger than the intermolecular force. But, like I said, it's the intermolecular forces that dictate the substance's properties, such as melting point, boiling point, and so on and so forth. Here's the thing to keep in mind. If the intermolecular force that we're talking about is very strong, such as maybe this one right here, if this attraction between these two particles was very strong, then think about it. It would take a lot of energy to break that bond. Which, if you think about changing from solid to liquid to gas, that would equate to higher melting points, higher boiling points, things like that. So that's something that you're going to want to keep in mind. So we now get to the three types of intermolecular forces for pure substances. So what I mean by that is, if we had a pure sample of a particular compound, these are the three intermolecular forces that could be there. What we're going to do is we're going to go through all three. We're going to define what they are, and we're going to define how you know what compound may experience any of these three types. Before we go into each of the three, it's good to know that when you are comparing molecules with similar molar masses, London dispersion forces are the weakest and hydrogen bonding is the strongest. So we see that relatively the strength increases as we go from 1 to 2 to 3. But like I said, that's as long as the molar masses are relatively in the same range. If you have a molar mass, let's say, you're comparing one molecule that's about 30 grams per mole, and maybe you're comparing it to another molecule that's, let's say, 250 grams per mole, I wouldn't say that that's similar. I'd say that's pretty significant. So we'll talk about some exceptions as well. Okay, so let's first talk about London dispersion forces. London dispersion forces, sometimes just known as dispersion forces. What are those? So they are defined as temporary shifts of electrons. They are temporarily shifted to one side of the molecule. As a result of that, that creates a temporary dipole, and we learned about what that was back in topic 7. A dipole simply means that there's one part of the molecule that's slightly positive, and there's one part of the molecule that's slightly negative. In other words, we create a polarity, right? And so what happens is, as two molecules get close together, the electrons shift. Why would the electrons want to shift? Because electrons are negative particles. So if you get negative particles close to other negative particles, they want to repel. They want to get away from each other. So if my hands represent two sets of electrons, if these sets of electrons get closer, these ones would want to repel away. And that's what creates the temporary dipole. So what I'm going to show you actually real quick is this blue picture right here is actually an animation. So I'm going to show you that right now. Alright, so I went ahead and made the PowerPoint live so you could see it. So notice when the two neon atoms are apart from each other, the electrons are relatively evenly dispersed. There's no dipole, there's no polarity in this particular particle. But when the two atoms get close together, do you see how the electrons shift? And so if we take a look at how the electrons are shifting, the side that all the electrons shift to is the side that's slightly negative, because that's where all the electrons seem to be congregating. The side that does not have any electrons is slightly positive. And notice, how are they aligning to each other? How are they attracting to each other? The negative on one side is attracting to the positive on the other. So just like what we learned back in topic 5, negative and positive attract to each other, right? And so that attraction is what's known as the intermolecular force, specifically in this case, the London dispersion forces. Now, what particles, how will you know what particles experience London dispersion forces? Here's the great thing. All particles experience London dispersion forces because they all contain electrons, right? And so because they contain electrons, they're going to experience that temporary shift. So every single particle experiences London dispersion forces, okay? So that's, at the very least, they all experience that. So let's talk a little bit more about London dispersion forces. What if you had to figure out, okay, great, yeah, all particles experience London dispersion, but how do you know which particles experience stronger London dispersion, because not all London dispersion forces are made equal. Well, let's talk about that. The strength of London dispersion forces depend on two things. The first thing, which is probably the more prominent of the two, is mass. The more massive the particle, the more electron shift it's going to experience, and so therefore it would experience a stronger dispersion. But the other thing that you need to consider too is also surface area, right? So the more surface area that a molecule has, the stronger the attraction. So let's look at some images to kind of relate these two things. So on the left side of the screen, you'll notice that we have 5 molecules that are listed, and they're all the halogen molecules. So you've got fluorine, chlorine, bromine, iodine, and astatine. Okay. You can see that their melting point generally increases. Fluorine's melting point is about 53 Kelvin versus acetine's melting point is 575. So it takes more energy to melt astatine than it does to melt fluorine, right? And same thing with the vaporization, same thing with boiling, right? Well, let's see if we can explain why that is. Well, if we take a look at the masses, so all of these particles experience London dispersion, right? But fluorine only has a molar mass of about 38. Acetine is about 420. That's pretty massive. So we can see that's why acetine has a higher melting and boiling point, higher or stronger intermolecular forces, because its mass is larger. There's going to be more electron shift from one side to another. Okay, so that explains the mass one, but let's take a look at the picture on the right. So on the right, you have 3 molecules. It looks like 6, but it's actually 3 because it's showing 2 molecules of the same compound, right? So we've got, the first group right here, and then the second, and then finally the third on the right. So it's saying, okay, if you had 2 molecules of each of those. All right. One thing to point out is that if it doesn't have it listed, but these 3 particles, we have neopentane, we have isopentane, and then we have N-pentane. Their molar masses are relatively similar. They have similar molar masses. It's not, like I said, that's not shown, but they relatively are very similar. But yet, neopentane's boiling point is only 9.5 degrees Celsius. N-pentane is significantly higher, it's 36. Why would N-pentane, that's on the right, why would it have a higher boiling point than neopentane on the left if they all relatively have the same molar mass, right? Well, it's because if you take a look at neopentane on the left, it's very clumped, it's very clustered, and so there's not a lot of surface area. So there's not as many areas for it to attract to a neighboring neopentane molecule. But if you compare that to the N-pentane molecule on the right, that molecule's stretched out, which means it has a longer surface area. There's more spots for a neighboring N-pentane molecule to have an attraction between, right? So we see that the more surface area that there is, the higher or stronger the attraction, meaning higher melting points and higher boiling points. So let's process through that a little bit. In example 1, I want us to take a look at 3 separate questions, and I want you to choose the molecule or atom that would be expected to have the higher boiling point, which remember essentially means the higher intermolecular forces. So remember, every single molecule experiences London dispersion forces. We just need to figure out which ones are stronger. So in the first one, we're looking at nitrogen versus oxygen. Remember, there's 2 things to consider. The first thing you should always consider is the mass. If I think about a nitrogen bonded to a nitrogen versus an oxygen bonded to an oxygen, surface area is not going to play a factor here, right? Because they're both the same length, So the only thing that's going to help me is mass. And if I take a look, oxygen has a higher mass. Therefore, it will have the stronger intermolecular forces, which means higher boiling point. In the second one, same thing. We're looking at a xenon atom versus an argon atom. Surface area is not a thing here. So it's only going to come down to the mass. And if I take a look at those 2, xenon is definitely more massive. And finally, we have CH4 versus C3H8. So we're looking at, a 1 carbon chain, which is CH4, versus a 3 carbon chain, which would look something like this. Drawing all those hydrogens. So in this one, C3H8, for actually 2 reasons. Number 1, this one's obviously going to have more mass, but it's also going to have a higher surface area. And so that's like a double whammy. It's definitely going to be that. So that covers the first intermolecular force. We'll finish up or continue in the next video.